So our goal is to solve this differential equation, this third order differential equation. But the first step I'm going to do is rearrange this so it looks something more familiar. So now we have a homogeneous equation to solve, so we're going to use the characteristic equation to solve it. So this is going to be r cubed minus 1 equals 0. The reason why it's minus 1 is because this y value has a zero order derivative, meaning it's not a derivative. Therefore, when we convert it to the characteristic equation, we simply just take the coefficient of that. Okay, so now we have to factor out this r cubed minus 1. It is actually a difference between two cubes, and if you go back to algebra, there is actually a formula that factors this quite easily. So that formula simply states that a cubed minus b cubed equals this. So we could rewrite r cubed minus 1 in terms of this equation. So we could say that the first root is simply equal to 1, and then to solve the roots of this polynomial, we have to use the quadratic formula. So we're going to say r2 and 3 are going to equal this. So then this equals negative 1/2 plus or minus I square root 3 over 2. And now we proceed to writing the general solution to this equation. So the general solution is going to simply be c1e to the x plus c2e to the negative 1/2 plus I square root 3 over 2, all this times x plus c3e to the negative 1/2 minus I square root 3 over 2, all that times x. So technically you could stop here, but I'm going to rewrite the general solution in terms of sines and cosines. So the first thing I'm going to do is rewrite this exponential in terms of a multiplication of these two different exponential values. So I basically just split up the exponential term. Now I'm going to factor out this e to the negative 1/2 x. Now to get this equation in terms of sines and cosines, I'm going to use Euler's formula, which says that e to the I theta is equal cosine theta plus I sine theta. So I'm going to use this equation to rewrite these terms. So this is what you get when you plug this exponential term into the sines and cosines from Euler's equation. Now simply all I'm going to do is collect like terms. But to do that, we have to relate this cosine negative square root 3 over 2x to the positive cosine positive square root 3 over 2x. And the same goes for the sines. We have to correlate these values so we could collect like terms. So the way I do that, I draw like a graph, and then I draw a line over here. And what we know is that the x-axis correlates to the cosine function, and then the y-axis correlates to the sine function. So I'm also going to draw a line like this, which is the complete inverse of it. So if we have, let's say, cosine theta, that's going to be the x value right here, and we'll say that's that value. And so the cosine of theta, that's going to go in this direction. That's a positive theta. So if we plug in a negative theta, we're going to rotate in this direction clockwise to account for that negative sign. And our x value is still that same length. Therefore, what we can say is that cosine theta equals cosine of negative theta. And now if we do the same thing for sine, so sine theta, that's going to be this right here. And then if we do sine of negative theta, so if we rotate in the opposite direction, that's going to be this value right here. So how those values are correlated is basically it's the negative or the inverse of the value. So what we can say is that sine of negative theta is equal to negative sine of theta. So these are basically some trig identities, and we're going to use that to plug in for these values over here to get rid of that negative sign within the parameter of cosine or sine. So this is what you get by using these trig identities. So now I'm just going to collect like terms. So this is what you get when you collect like terms. So the one thing to point out is that c2 plus c3 is just some arbitrary constant. So I'm just going to call that c2. It doesn't really matter what you call it, but I'm just going to call it c2. And the same actually goes for this value right here. We can just call this some arbitrary constant, because remember, I is just any other number. Although it's imaginary, it is just a number. So what we can do is call this c3. So now that we have all that defined, now we could just rewrite this general solution, and that'll be the solution to the problem. So that is the solution to this differential equation. So hopefully this helped you on how to use Euler's formula and apply it to differential equations. If you have any other problems or suggestions for differential equations, leave them in the comments below. I'll be more than happy to make a video to help you out. With that being said, I'll see you in the next video.